doing nothing for a bit. Here early just for that. So today this will be all about embedded programming. So this is a really key part of the whole class because your robot, you'll be doing the electrical engineering design for the hardware and stuff like that, but it won't really do anything unless you do the programming aspect of it, or at least one of the two of you does the programming aspect. Ideally, both get involved with that. But this is, it tends to be for almost any field you go into in electrical engineering, there ends up being programming. So if you really hate programming, there's sort of very limited fields that are pure hardware. So it's good to know this type of stuff and get into it, even if you don't immediately plan on using it. And today I'm going to be covering a bunch of stuff. So a C code refresher, we use C or C++ for the Atmel processors. That's probably the most common, or is the most common, embedded language. Both C and C++ are still widely used. So that'll be sort of a quick refresher. If you have never done C before, it'll give you an idea of what it looks like. I bet you'll need some time, to go through some examples on your own. I'll talk a little bit about what it means running C on a microcontroller. Some pretty basic embedded design methods to give you ideas for your project. Some stuff on coding standards. I'll talk really briefly about an example framework. I'll probably push that till Monday or the lab. And then a few interesting other topics about code, static analysis, which helps you find bugs in your code, and code documentation. And there's actually a third thing here that I'll show you at the end, which is revision control. So how you manage all your code between the two of you or in larger teams. All right, the first part, C code refresher. So I have a little caveat here, is that learning C code takes years to do even remotely properly. And this is like a 15 to 20 minute real quick overview. So don't expect that this lecture will be all you need for C code. It'll take, even if you've done it through school, it still takes years typically of experience in the field or just writing systems to sort of figure out all the nuances of C and get a better handle on it. So there's a bunch of other languages that people, if you haven't used C, you might have used. How many people haven't used C out of interest? A few people, I thought. I guess probably a lot of the classes in here too. So if you've used these other languages though, there's some relationship between them. So C is typically seen as sort of the base, one of the first languages. From that came C++, which basically added an object-oriented nature to it. For most of the embedded aspect, the amount of the C++ extensions that you'll be using from C is so minimal that you can really use either. The compiler will happily handle both. So if you know C++, you're fine. The other popular language that people might have used, coming from sort of the hobbyist side, is the Arduino language, I call it. Not really a language per se, but the interesting thing is that Arduino is really just C++. So if you've written any sort of Arduino code, this is, very basic C++. They try to hide a lot of it from you, but if you look under the hood, the Arduino system is basically just pulling in C++ libraries, compiling it for you using the same compiler we're using, and then gives you a file that's programmed. So although the flow won't look the same as Arduino as what we're doing, it's effectively the same thing. Arduino tries to simplify things and to some degree hides stuff from you that we'll need to access, but the basics can be the same. We keep going up the chain to higher level languages. So Java is used in embedded systems. It's used in larger embedded systems typically. So like, a lot of phones are running Java. Other small embedded systems, set-top boxes, stuff like that will run Java. I think, they always have some stat. Whenever you're installing Java and it throws the facts in your face, it's like billions of devices run Java and stuff like that. So it's used in a lot of systems. The next two languages are not really used for embedded systems too often. So Python is one sort of higher level language. That's pretty popular on computers, scripting, analysis. You can write huge programs in it too. It's a great language if you haven't used it. But there's a very, very limited applications to embedded systems in terms of directly running Python on something like a microcontroller. There is some efforts to actually make Python run on microcontrollers, but it's fairly limited right now, fairly niche. And the final one I'll mention is Matlab. So again, this is a language that within school, a lot of people will have used. It's almost never used directly in embedded systems. Matlab does have compilers that will take your Matlab code and write C for you, which, I don't know, we don't really talk about that too much because most people aren't using that. For some types of systems, if you're trying to do like dynamic control systems, that can be useful, but it's not something we really concern ourselves with. However, the syntax, if you use MATLAB, the idea of loops, variables, all this stuff, you'll be able to apply over to C. So if you know any of these languages, it's some help in learning C. If you basically know any programming language, it's going to be useful understanding C as well. A basic C program can look something like this. So this is some really dumb robot example. And what we see is that we have what's known as the main, this main loop in main void. So this is automatically called when the program runs. We have some variables. So this is an integer type. So there's different variable types you can see come in the front. At the other side, we have the variable name. Later, I can call, for example, functions. So I have this setup world function, which is defined elsewhere. Oops. Try not to write all over everything. So this setup world, so this is going to do whatever the hardware setup's required in our system. And then we just have a while loop. So this while one is an infinite loop. And again, this is something you'll often see. So at this point, the system's just going to do these instructions and keep repeating forever. So this would be like the main loop of our robot. It's just going to continually do these tasks. So you can see it calls this getRange function, and it assigns whatever the result of that getRange function is to the that variable I declared. It turns the motors on every time through the loops, and if an object is too close, I have this if distance centimeter is less than 200, turn the motors off. So it's sort of a dumb loop because A, it's always turning them on, then right away again turning them off. And all it's going to do is drive and then sort of stop at some point. So not the greatest robot in the world, but it gives you the idea for what a C program looks like. So if you want to play around with C, you can install compilers on your computer really easily. I believe you have access to some of the Microsoft tools, Visual Studio, through the Design Spark, or I don't know what they call it now. But does everyone know about that? There's a way Microsoft gives you free stuff. DreamSpark, yeah, that's it. So if you don't know about that, you should, because you can get a lot of stuff. Like they used to have Visio on it. If they still do Visio, Microsoft Project, so these are worth like $500 or more to buy, and you just get it free as a student, and it's a full license. So even if you don't want it, you should just install it, because who knows, you might. Anyway, so if you don't want to do that, another thing I'll show you out of interest is there's various websites. So I just picked one at random, C++.sh. So this is actually a C++, supposed to be a C++ compiler. All C is valid C++, so that's fine for us. So if you want, if you're like, I could try doing some C coding. So if you look online and find tutorials, like there's always the hello world. Can you sort of see that? So if I write a little crappy program here, hello class. Oops. And I'll return -1. There we go. So you can write a program and you can run it right in your browser, and you can specify some options that I'll talk about in a bit. And if I screw up like I did here, it'll flag errors for you. run it again, and then it executes it. So normally if you ran it on your computer, you can see some output on your console, so I just have this hello class that it prints. So this is a really easy way, if you want to like, Google some C tutorials or something, that's a good way to run them, just as a side note. So the compiler is going to take that C code that I wrote. So the previous example was a really simple hello world or hello class in this case. And if there's errors in it, what it's going to do is flag them. So it's either going to call out specific errors. So I have another example program here where there's some functions I called that were not valid, that I hadn't declared what were, or stuff like that. There's another one where I tried to assign a variable that I didn't provide. So those are errors and will stop your compilation completely. It also gives you some warnings, so you'll see this warning, unused variable. So for this stuff, it's typically the compiler saying you're doing something that looks like it might be an error. I don't know for sure, but you should check that out. It is always worth, the problem is that you can compile, it'll print a bunch of warnings, and you can ignore them because it still generates a file you can use. But of course, a lot of the time, those warnings were actually important, so you shouldn't get in the habit of totally ignoring them and just saying, okay, great, it worked, let's try it. It can get very frustrating if you do that and things aren't working, you don't go back. So you should always read through these, and you can sort of get a feel for where they come from. In this case, it's telling me I didn't need to use this variable, perhaps, because I assigned it a value and never touch it again. So when we're talking about C, we have these C files I showed. So this is the C source. You'll also see what are known as H files. So these are header files, and I'll talk about that in a second. From those two files, it's going to generate a bunch of other stuff. Some of them you don't care about. So one of them is, you'll see these O files. These are what are known as object files. And these are part of the binary. So when I say binary, that's like on Windows, you have the .exe that you double click and run. And this has all the instructions for the microcontroller. For our little devices, we're going to deal with these hex files. These are what we program in. So what is programmed? And you can call that a binary. So to generate that, it creates some other files. These object files are individual files that have some of the code in it. It combines all of them. Ooh, crap. Combines all of them into what's known as an ELF, which is just its own internal format, before generating this hex file that we need. And another one that we will talk about and hopefully see in the lab a little bit is what's known as this listing file. And this file includes information on what the compiler did. So this means that it has the assembly instructions, which is it has the instructions the microcontroller is actually running. So if you want to see like, oh, I wrote this C code, what is my microcontroller actually going to do specifically, that gives you information on that. Most of the time you won't care about it. Ever so often it's useful. So it's good to remember at least that it exists, if nothing else. All right, so that's a quick idea of what the compiler inputs and outputs will be. So the C file I showed you before has all your source code in it, and at the top of it we see these includes. So these includes are where the header files come in. So you can see this like motordriver.h, rangefinder.h. So these are header files that the entire file gets taken and shoved into your C program. So all of this data, is in fact copied by the compiler and put. So if this was rangefinder.h, it's literally going to replace this line with everything that's in that other file before it continues. So it's just going to take that file and paste the whole thing in there. This is all seamless to you, so you don't see this happen. And this is what the file would typically look like. So I declare that, hey, I have this function called getRange. This function, gets the range from the rangefinder and returns it as a unsigned integer. So it just tells the compiler and you some information about what the functions do. So all of this stuff is done through the preprocessor, that include system. So you can see it's a preprocessor. If it has this hash command, it means something's being done by the preprocessor. So when I see preprocessor, what I mean is that we have this file. Anytime you have this hash, something is going to happen before your code gets compiled. That is, before it gets generated to a binary. So the include means include the entire contents of that file. Normally it's this .h. You could include any file you want, and it'll just copy the whole contents in there. We can define constants. So I have this, start or hash define L gain 4.5. So from now on in the C code, I can just write L underscore gain 4.5. Why you might want to do that is, oops, did I even have an example in there? No. Why you might want to do that is that if you have some code, for example, you might have something like y equals, sensor, and this is a function, so it's reading the value of a sensor, and I need to apply an offset, 4.72, and that's a floating point. So I have some line like that, and 4.72 is some mystical value, some offset that depends on the physical system. So rather than do that, I can write y equals sensor plus, and actually give it a name, offset, sense1. And ideally this would be, like front sensor, offset front sensor for whatever range, whatever it is. And all that means is I had to do it earlier, start define, offset, sense1, 4.72. The code's more obvious what the heck, that value was, offset sense1. And B, I can put at the top of the file all of those offset defines so that, if there's a bunch of sensors, I can see where all my offsets are, and it's a lot easier to go through. We can also use the preprocessor for sort of these cheater functions called macros. So you'll see these throughout too. The difference here is you notice I have the define has brackets on it. In this case, there's no arguments or anything. So all I've done is I've made this function called LED on, and really all it's doing is some C command. In this case, it's setting bits in a variable, so we're in a register. We'll talk about that later. But I can make it do, whatever I want. And the preprocessor is literally just taking this and copying it and pasting it in every time it sees this LED on. It's not a function call. It's not doing anything besides taking that and pasting it in. It doesn't do any check or anything. It just pastes it in for you. So it's just a little copy replace, effectively. All right, comments. The other thing you'll see in C codes is these comments in green. So the comments are stuff that is for people to help them understand what the heck's going on. So there's two types of comments you'll see. End of line comment, so the double slash here is an end of line comment. And this means from now until the total end of the line, everything's a comment. So in this case, I have it above the line, but I could have put it here, for example. We can also specify that only within some area is something to comment. So where the difference is, open a C, might be a little hard to see. Okay. So to give you an idea, if I set this to C++ mode, so I could have a line like, x equals y plus 4.72. So if I have an end of line comment, some comment, you can see everything is a comment. It's showing up in green, means it's a comment. with the other type, so if I couldn't, what I can't do with that, for example, is make a comment here because it just eliminates the end of the line. With the other type, I can put a comment within a specific section here. So I can put here is another thing. And the compiler is just ignoring that middle part of the code, and it continues to parse. So this will compile just fine. So that type with the slash, let's pull that back. Ooh, crap. All right. Yeah, so that's the other type of comment, is where you define specifically where it is within the system. So the only thing with that type of comment is what people will do sometimes is you have some code, and what you want to do is you want to disable this whole code. You want to say, actually, don't run that right now. So what you're trying to do is basically, you see this comments out that whole section. The whole thing turns green. And if I had the end of line comments, that's fine, because the end of line comments just mean that whole line's a comment, that's it. If I tried to do it with the other format of comments, what's going to happen is it's going to start the comment here and then end it here. And then there's going to be this extra, it's going to give you an error because there's an extra end of comment string at the end that it won't know what it was doing with. So that's sort of the only thing offhand to really watch out for. The other thing with comments to watch out for is, one thing you'll see people do is, if I go back to Programs Notepad, we talked about the macros. So what you'll often have is something like, star define gain sensor 47. So I have this macro, and it says, okay, define gain sensor 47. And later I have y equals sensor plus gain sensor. So I have a nice little code, that looks beautiful here. And I say, hey, I want to tell people what I was doing. And I say, based on experiment. Let's go over here. So I write a little code like that. And when I try to compile it, it's going to give me an error. Why it's giving me this is the preprocessor is not smart. It literally takes everything after this, copies and pastes it in here where gain sensor is. So when it does that, what you can see happened is it commented out the whole rest of that line because it copy and pasted your comment as well. So the only other thing to watch out is if you're using the preprocessor like this, either use this type of comment or move the comment to the line before. Because if I had this type of comment, it would be in line and there's no issues here. So that's sort of another problem you might run into to watch for. Ooh, crap. All right. The other thing you can do, so when I talked about commenting out, if you have a section of code and you say, like, actually, I don't want this code to run right now, if you turns on all your motors and the robot's sitting on your desk, the safest way to use this is use the preprocessor. So the preprocessor has some system that allows you to selectively include or remove code. So if you put this #if statement here, what it's going to do is everything until another endif will simply not be part of your code. If I want to include the code, I can just change that to if1 or just delete it. So as an example, if I wanted to remove this, I can just go if0 and if. And now that section of code won't be included. Some people don't like it as much because you notice if you look at a glance, it's harder to see that code is not included. Nicer IDEs will actually gray that out so you can really quickly see that that section of code isn't there. So if I wanted to put the code there, I could just put an if1. And now everything from the if to the endif will be included. So there's going to be a whole bunch of headers you're going to run across. that you'll see used in the various projects. So depending on your project types, they may either be the AVR libc headers or the Atmel software framework headers. They're all available online. I won't go through them right now. We'll see a bunch of them in the lab and stuff like that. All right, so the other thing that's useful to know about is the data types you're likely to run into in C. The basic types are, you always have your integer and unsigned integer. Now, what is an integer? What is an unsigned integer? On the AVR and the devices you're using, an integer is 16 bits. So you have 2 to the 16 storage. If it's signed, it's somewhere around minus. This means you can store a number from minus 32768, is it? I think, does anyone know offhand? To positive. The one side's smaller by 1, and I never remember which. I'm going to say 7. One's minus 7, one's plus 8. I can never remember. So it can only store a number within some certain range. On larger devices, the integer actually may be bigger. So you take the same code, you compile it on your computer. Your integer may become 32-bit or 64-bit. This is because the integer depends on the natural integer size of the device. So if it's a 32-bit or a 64-bit device, that's what your integers will be. It's never smaller than 16 bits. AVR is an 8-bit machine, but an integer is defined by the standards to always be at least this size. The problem here is that you could take your code that works on one device, try to compile it on another, and things start breaking because you don't know offhand exactly the size of the integer. So something I sort of recommend is using these macros here. So to use these, you have to include a header file. So what's known as the standard integers, standardint.h. And they give you these other data types. So this uint32_t, for example, is always an unsigned 32-bit integer. What this lets you do is say, if I need to store a large value, I can force it to use a 32-bit integer, always. And same thing for 8-bit, 16-bit. So on the AVRs, it's always a good idea to use a int8 or uint8 if possible. The reason being the AVRs are 8-bit machines. This will be the fastest and most efficient because it can naturally add 2 8 bits, multiply 2 8-bit numbers in a single instruction. This of course is completely dependent on the fact that you can store whatever you need to store in the range of 0 to 255 inclusive. So it can only represent a number within that value. So if you need to store a larger number, you're doing a calculation. If you're doing a rangefinder, for example, the 8-bit isn't going to be an okay method because you probably will have a longer range than 255 centimeters. I think they go out to 4 meters, for example. So there's a lot of considerations there. But the important thing is that using these lets you specify exactly what I'm getting. Without any issue, if you ever need to move the code, what size integer you're going to get.
I have a question about performance for those.
Yep.
You said that on an 8-bit processor, the 8-bit data types would be the fastest. On a 16-bit processor, would 8-bit data types be slower?
No, it will. Basically, you won't lose anything. So typically, it depends a tiny bit. The general answer is no. If you request an 8-bit integer, like on your computer, so if you take this code, your computer's a 32-bit machine, you request 8-bit integers, normally it just uses 32 bits internally because all its registers are 32 bits. So it has no way to just operate on 8 bits. And it'll just ignore the top part of it, so it just uses that 8 bits. There can be some penalty if you specifically ask it, like, I want 8 bits only, and like shoved a bunch of 8-bit numbers side by side. There can be some issues there because it will actually have to go out of its way to say, oh, you want me to put an 8-bit number right beside an 8-bit number, right beside an 8-bit number, right beside an 8-bit, right beside. which it's not designed to do. It's designed to put a 32-bit number or a 16-bit number beside each other. So then it has to do some extra instructions. If you're just writing general code, and you're not requesting that, there shouldn't be any penalty hit. It's just wasting, the possible resources. But if you don't know for a fact you only need 8 bits of data, there'd be no difference, in that case. So, oops. Other. I can never get out of there. We go. All right. C on your micro. So C on the micro is very much the same as writing C on anything else. The main difference is you're going to be doing lots of writing to special registers. So these are defined in the data sheet. So for example, come on. If you look in the data sheet, there's like a data A register. And all you can do is if I have port A and I want to assign it some value, I can just write a value. So this is hex FF, which would be all ones, by the way. So there's lots of hex used in C code. You'll see all over the place. So that means I'm just setting every bit to 1. If you want to set individual bits, the easiest way to do it is, this is sort of the normal construct, is, you can see it. The normal construct is something like this. So all it means is that I'm taking the value in the port. Whoa, this doesn't work very well. Okay, I'm taking the value in the port, and then I'm ORing it with, what this means is 1 shift left 4. Okay, I'm going to take that off. 1 shift left 4, so it means I've taken, if I write down, 8, if this is an 8-bit, 1, and then I've shifted it left 4 places. So if you shift left once, twice, 3 times, 4 times, it just means I'm setting this bit here. So bit number 4, again, we're starting with bit 0 is the count. Bit 0, 1, 2, 3, 4 is being set to 1. So it's just going to take whatever value's there, OR it with this, which is this constant here, which will mean that bit gets forced to 1. So we take the existing value, we set the bit 4, again, starting from 0 to 1. And you can chain that to, for example, set bit 4 and 5. So if I want to set both of these bits, this construct here would do that. And because we're ORing it, remember, if the initial value of port B had some other bits set, they're going to remain set afterwards. So all it's doing is setting some bits. The other thing you'll see is there's a clearing bit, a fairly common construct. And the difference here is we're taking the value of the port, so in this case port B, and I'm ANDing it. So if, for example, port B was 1100, I should make sure it's set, 1110000, and again, we want to clear the 4th bit, counting 0, 1, 2, 3, 4. So we want to clear this bit. What we're going to do is we're going to AND that with 11101111. When we do that AND, what we end up with is that bit cleared, and any other bits that were cleared initially remain cleared because of the AND. So the little bit of code to do that is this thing here. What this means is that we take that same 1 shift lefted 4, so you end up with 0, 0, 0, 1. So that's the 1 shift lefted 4. The little tilde, I guess you'd call it, this guy here, means bitwise inverse. So we do the inverse, we get this, which is what's fed into our AND. So that's sort of how you read the clearing bits construct, and it's typically written in a sort of shortened form like this. So this would clear bits 3 and 4. Bit 3 is already cleared, so it wouldn't matter, because it's going to take port B, and again, you have to pay attention to where the brackets and the tilde is, but it's going to generate this string with bits 1 and 4 set, do the inverse to generate a string where only those bits are 0, and it with the original. The final result is bits 4 and 3 get cleared. So you'll see this type of construct basically everywhere in embedded systems. So you'll want to be able to recognize really quickly what they're doing. They're clearing bits or setting bits. It's definitely one of the most common things you'll see in all embedded code, I'd say. For AVR specifically, so these constructs are everywhere, not just AVR. For AVR specifically, you're likely to see in certain code other special macros or other special what look like functions. So one of them is SBI, which is set bit, and this is the AVR. You used to need to use this to set a bit due to some restrictions in how the system, the compiler worked. You no longer need it, so it's just legacy. All it does is, so we have this function, and it actually gets replaced with that same construct I told you. So if I called, for example, SBI port B 4, the preprocessor is actually going to chunk port B into this macro here, and we'd end up with the same thing I showed you in the previous slides, and then compile it. So there's really no, you don't need to use these. You can if you want. They're still there. I believe they're marked as obsolete, so they might get removed at some point, but all it is a set bit and clear bit macro. Again, you can use it if you want to make sure, oh, I might forget the little tilde or something like that. It's a good way to ensure you never forget that, because when you're looking through the code, it can be really hard to spot this missing tilde, because it'll compile it just fine, it just won't work. The other thing you will see a lot and is still actively used is this BV_BV macro, which stands for bit value. And all this is doing is this is replacing the shift left with a little call. And why you do that, it's basically a matter of preference. So here's 2 examples. So here's with the BV macro, here's with the normal shift left thing. So the idea is that you can kind of pretty quickly see, okay, we're setting bits 1 and 5, or we're clearing bits 1 and 5. Sometimes it can be confusing, especially if you see stuff like, 1 shift left 0. You may have to read it for a second to say, wait, is that bit 1 or bit 0? If you have the _BV, it's very clear if that's bit 1 or 0. It's purely a preference thing, but you'll see it in a lot of code, so you should know about it, and you might want to use it. The other thing specific to the AVR, but also generally in embedded systems, the bit names you'll find used throughout the code. So if you look in the data sheet, if you look at a register, you say, I want to use the some system, and you read through the description, and it says, okay, to use the system, you need to set the TWEN bit, and in this case, I'm setting, for whatever reason, this TWINT bit. So I need to set these 2 bits. You could look at the data sheet and say, okay, that's bit 2 and bit 7, and write this code here, which is perfectly valid, but it doesn't mean anything to anyone. Bit 7 and 2. So all of the header files by default include names of the bits, and these are just defines that say this is bit number whatever. So this will be 2. Is all it means. It doesn't check you've set it in the right register or anything else. But it looks a little nicer because you can look at your code and you can use the BV if you want with these 2. So I could have also written _BV. TW enable or TWN. It's just a little nicer, and again, something I really recommend using in your code to make it easier to understand when you're going through and debug. All right, so that's a super quickest introduction to C I could do. Are there any questions, though, about C before I move on? We will have more chances, obviously, to work with it throughout the whole semester and tutorials and stuff like that. But anything I grossly missed? Okay. If not, some really basic programming rules. This is sort of generic stuff. But basically, if you're writing tests, you're writing, you're trying to get something working, always reduce things to whatever the minimum possible set that will or will not work. So you're writing your code, something breaks, figure out what's the smallest amount of code you can, write that'll cause it to not work or cause it to break. Basically, if you just have a huge program and you come to the TAs or me or say like, oh, it doesn't work, I have no idea. No one's going to help you because they'll have to go through and look at everything. You have to figure out, oh, this interrupt is not firing. I'm going to delete everything until it's just the interrupt should be running. It's not running. That's the problem you can then solve. You can't solve the whole system not working, but you can solve, small code samples. So it's really important to always keep that in mind. And we'll talk about debugging a lot more on Monday, but small code samples are what you want to keep everything in. The other thing is it's always important to test things. So even if you have some very basic code that, set some bits, waits for something to happen, you'll want to test at some point, hey, that's actually working right. Just because it looks right on my screen, I don't want to assume, that it was fine. There's always going to be these really dumb or frustrating mistakes, and it's always going to happen, like you forgot a semicolon at the wrong spot, and it didn't quite do what you wanted. As an example of that, to give you why I say like always test things, let's do a little demo here. Come on. So if I have something, and there'll be some more demos at the end. In C, we could have an if statement, if y is smaller than 45. And in C, for if statements, we have two options. So we can have these brackets, and we could call a do something. Oops. And I'm going to make this a macro for a reason. We could call do something. Now, if I was lazy, I don't actually need these braces. I would always recommend having them. But this will work just fine. It'll still call do something. But if I later define do something, if I'm using a macro, and I'm going to try and be clever and actually chunk two function calls in here, whatever reason. So init thing, do thing. So what's going to happen is, I needed to change it later so that it calls some initialization code and then does it. If I just looked at the if statement, it sort of looks like, okay, that's really simple. I don't need to test that. That's going to work. The problem is that when this gets chunked in, what's actually going to happen is due to how the C code works, that's basically what's going to be replaced with. The if statement will now always execute, or do thing will always be executed because it will fall outside of the if statement, and init thing will only be called when y is below 45. Otherwise, do thing's always going to be called. If you're in a panic trying to get something working, you might think like, oh, it's it's a one-liner. I don't need to test that. But you should always do these tests because if you make simple assumptions, something like this, you could spend hours thinking it's some other problem when it's just a small problem like that. All right. Embedded design. So how not to program. There's lots of things where you spend so long doing debugging that it's just gonna continue going into your development forever. So I want to do very briefly how not to program and how you should program. These are all very generic rules. The first mistake people will make is they'll use their programming language as a design language. So when you're thinking, okay, I'm going to write a program that's going to drive this robot, you shouldn't design it in any programming language at all. design should happen basically with pen and paper, or written down in a human format. So what you want to say is stuff like drive forward, and it doesn't even have to be look around, drive left if open. So that's like a really simple sort of start of the design language. I might take that, try to make a flowchart out of it, but you don't want to be too formal right away. At the beginning, you're just thinking of ideas. This goes back to the design process. We're trying to really quickly iterate through, okay, let's think about what we do, maybe do some quick proof of concepts, write some simple code to test them. Once we have that, then you can move on to implementing it in C. But one of the biggest mistakes you can make is starting right away to write stuff down and trying to get your robot moving and hacking on, being like, okay, well, it can look left, now let's figure out what we can do with that. If you start with a higher level plan, you'll save a lot of time in the end, because you'll be able to quickly decide, is this doing what I want roughly it to do? If so, okay, let's improve it further. To do this, one thing we're going to hopefully use in this course is this event loop structure. So basically what we're doing is, you can see at the beginning we have, so there's the standard C stuff, header files, blah, blah, blah. We then have some calls to initialize everything at the beginning, maybe some other stuff to set the motors up. And then we just do this loop of processes. So this loop is doing things like reading the sensors. Once it reads it, it's doing the navigation, it's doing the movement. And it just continually does this in one big loop. And this sort of event loop structure is what you'll very commonly see in embedded systems. To the point that things get moved to a real-time operating system is the next step up from a simple loop, where you write your code in tasks. So in this case, each of these, reading sensors, navigation, is a task, and the operating system is responsible for switching them for you. And the real-time aspect of it is different from an operating system like Windows or whatever. The real-time aspect of it means that we can guarantee a task gets run every so often. So we can say this task has to get run every 100 milliseconds. And why you want that is, for example, if you had a car, you might have one task that does stuff like check radio button. So you're checking if the radio button hit, which would be volume or changing the station. And you can do that every 500 milliseconds, and the user won't get too mad. But on the flip side, if you're, for example, checking check brakes, check if the user's hitting the brakes, you probably want to do that every, more often than 500 milliseconds ideally. So you might say, well, we're going to do that every millisecond. And if the user's starting to hit the brakes, we're going to, if we have a traction control or something like that, it's going to start taking corrective action, doing what else if it's a hard braking condition. Obviously, in a real system, there wouldn't be one OS for the whole car, but the idea is that we can assign tasks different priorities. We can force some to run very often, force some to run when there's time, stuff like that. So the real-time operating system gives us that ability. The other thing you might want to consider is looking at coding standards. So what these are, and I'm just going to use an example one I found. What these are is ways to ensure sort of like things look consistent in your code. So there's lots of examples of them. I'll just pull one up randomly. And so it has stuff like, and you can look, there's official ones for certain specs. You can look online for various ones, but it has stuff like, when you have variable names, include the names, the units in the name. So if I'm making a variable, I have a timeout in milliseconds. I have a my weight in pounds. So these sort of coding standards will have all sorts of stuff we'll go over, like if you have multi-barred names with multiple, words in it, we're using an underscore to separate the name components instead of having capitalized letters. So there's a whole bunch of stuff you can go through. if you're interested, and it is useful to sort of get an idea how to keep a consistent naming and code structure. It will make your code look a lot more recognizable. It's a lot faster to for someone else to go in and see what you're doing. You can always have personal preferences, so just because you're using one, don't feel like, oh, I always have to do this. Some people, people will have huge arguments on the internet about like, oh, you should be using 5 spaces or 4 spaces instead of 8 spaces for everything. This is like, I'm not even joking, this is a real thing. And it's crazy, but it's really a lot of personal preference. It doesn't matter too much as long as things are fairly consistent, the code's reasonable and readable. That's the most important part of it. So if you want to use one, definitely you should look into it. I really encourage you to, but don't see it as its iron rule. See it as ideas to help you improve your code, not necessarily something you have to use all the time. All right, so I was hoping I do have time to get to this, which is good, because this will be something that is hopefully quite useful. This is about static analysis. So the problem is that back when I was talking about, don't design in C, you design in thinking what you want. And there's a bunch of steps when you're doing this. So we have the initial specification, which in your case is, what you need the robot to do. You're going to make a design for, okay, here's what I want it to do roughly. I want it to drive and look and then drive into this wall and then back up and then drive into the other wall and then back up. Hopefully more than that, but whatever you do, you have a design. You are then going to implement it in C. So you're going to take that and you're going to say, okay, here's how I'm going to code it in C to do that. Finally, the compiler is going to take what you've told it to do and generate an executable. Hopefully, there's no errors in the compiler that introduce bugs. But we've got a lot of steps. So this is what we need it to do, and down here is what it's actually doing. And every point in between that 1 and 4 is a chance for bugs to creep in. And there's a lot of chances for bugs to creep in sort of right at this interface here. Because you're going to be thinking, when you write the code, you're naturally going to be thinking about your design. You're going to be thinking, okay, I want, these variables to add and these to multiply, and that'll work fine. The compiler has zero idea what your intentions were. All it's doing is it's looking at the code and saying, you told me to do this, and I'm doing this, and it's your problem if it doesn't do it. So it'll happily correct things. That the syntax is perfect, but the design, is incorrect or something like that, or it's doing things that you probably don't want it to do, but you told it, so it's what it's doing. So what we have is instead we have a tool. The tool still doesn't know your intentions, but the tool can detect what are probable, what look like problems, what look like things that are odd that you probably don't want to do, and it'll tell you about it. So there's something called lint. For this, and I'm going to show you PC-Lint, which you can use online loosely to do some testing. So as an example, I have this C program here, and what I've done is I have this sum20. So I have this routine, and what this routine does is you can, What this routine does, is it takes some array with 20 elements in it, adds them all together, and then returns what the addition is. So sum20, very uncreative name, but it does what it's as advertised. I'm then exercising it with it, and I have a routine that loads 16 bytes into an array, and then adds them up. And because I was, being lazy, I wasn't paying attention, and I called this sum20 on a device which only has 16 bytes in the array. So what this means is that in the compiler, it's only allocated 16 bytes. And there's still 4 extra bytes, and this is just random. Because it's just some garbage. It's just whatever's on the end of those 16 bytes. I have no idea. It's going to depend on what my computer was doing before. So when I call this sum20, is actually going to operate over everything, over 20 bytes of data, and could possibly return invalid, invalid stuff. The problem is that it's not reliable. So if I ran it one time, I ran it here, and it returns 120. So if I had a unit test, it would say you're an awesome programmer, everything worked fine. There was no warnings thrown by the compiler because everything I did was perfectly legitimate. So it has no idea that there's this huge error in it. And this type of error comes up a lot. This is sort of the buffer overflow. The heartbleed error was related to something like this. Not quite the same thing, but the idea is where we're reading too much of a memory array. So if we can find those problems, it's going to save you a lot of hassle, because this won't always work. This worked in this case, and it worked in this case because these random bytes were 0 here, but there's no guarantee of that. It could be after a while, those bytes have data in them, and then it throws my sum off. So how we're going to fix this is use a program called PC-Lint. And so PC-Lint actually walks through my program and detects a lot of these problems. So you can see here, it's actually it's given me a warning, possible creation out of bounds pointer, 4 beyond end of data. So it realized, hey, there's an issue here. You're calling a function where you've defined a smaller buffer than you go to use. So it does more than just checking syntax. It is actually looking through the program at what the program's doing. And you can see it flags lines 14, 23, and 24, which is both the line where I call the function along with the lines where I use it. It also tells you some other stuff I did that was possibly an error. In my case, it doesn't matter at all. So one of them, loss of precision, 31 bits to 8 bits. So it's telling me, hey, you declared I as an integer, and now you're assigning it to an 8-bit, number. Test data was declared as an 8-bit array. I is 32 bits. Something's gone wrong here. In this case, I don't care because I know I is always from 0 to 16, so I could ignore that, and you can set a flag to turn that specific warning off. Another example is loss of sign. So I'm returning I've taken an integer and I'm returning an unsigned int, so I'm throwing away all the negatives. Again, in this specific case, I know that's fine because I'm always adding up unsigned numbers, so I could put a note that says, okay, this is fine, ignore that. All right, so the previous example was sort of, if you look really carefully, you could find that eventually. Here's a trickier example. So here is a program that calculates what the average temperature is, and let me run that program real quick. 5 minutes left. Actually, I have it. So if I run this program, so what it's doing, you can see, is I have the temperature in March, and I add up the temperature in March, so sum March, and then I divide the sum by how many numbers were. Very straightforward. It doesn't look like any serious errors here, so let's run that. And whoa, that's clearly an insane number here. Something's gone wrong, and there's no warnings. Even if I turn on all the warning flags, I don't think it'll give me anything. Yeah, so the compiler doesn't tell you anything. It's wrong, and it looks fine. There's nothing that looks wrong that terrible there. So if I go ahead and throw it in to PC-Lint, so PC-Lint, there's an online forum that you can chuck some of this stuff in. Let's try it. So if I copy that code in and hit analyze, it's actually, again, trying to find some of these trickier errors. And in this case, what it's flagged is it said signed, unsigned mix with divide. So what's happened is one of these variables is signed, one of them is unsigned, and the compiler is converting in a way we might not expect when it does this. So we can see count is unsigned, because that's just how many there were, so it made sense to make that unsigned. And sum is signed, because it's an integer and it might have negative or positive. So that's a really, it seems fine. When we wrote that, it makes sense, but it's telling us specifically, hey, this is not good because you're mixing signed and unsigned with divide, and what's going to happen is it's going to convert that negative number to a positive number in a way that you're not expecting. Basically, the compiler is just going to read the bits as if they were a positive number, and you get this huge number. So we can fix it just by adding in C, forcing that integer, that count, to be an integer. So let's just fix that in the C++ shell. So there you go. So the average temperature was 0 degrees. This is all integer mass, so that's as close as it gets. So there you go. So that fixed it. So you can use the PC-Lint to check your own designs, and basically you can get standalone licenses for it. The easiest thing right now is you can just go to the web address, this Gimple Online. They have a whole bunch of examples, as well as a spot that you can just copy and paste code in. And you can do multiple files with some work too. So I think one of the assignments will have something on that. But it's a really great resource if you want to check chunks of your code. All right. So the final thing I'll cover, very briefly, there's something called Doxygen, which you may again find useful. This is for documenting your code. So this allows you to generate documentation directly from your code. This is an example Doxygen page I created for some project, and you can see it looks pretty nicely. It has all the, I can talk about the different devices in it, the architecture, and each of those links is basically a documentation page that can describe what I'm doing, and more importantly, every function, it describes what that function does. And I can even add in references to what other functions it's calling. So there's sort of a call graph you can't see to the bottom there. And it tells me, if I want to send this echo request, there's these variables. Here's the type. And I have a nice little thing that says ifnum is what interface to send on, the destination address, and all this stuff. And this is all generated from my code comments. So there's sort of a special structure to the code comments. So you can see, for example, I have this @param, and that's just a flag to Doxygen to tell it, hey, this is a Doxygen thing. And the other thing Doxygen uses is, you see this double arithmetic at the top. And this is how it means the following code block is special, so you need to pay attention, Doxygen. If you don't have that, it just completely ignores it. Oops. And then you can see I have the parameters. And so you can just run a command that searches all your source code and generates these HTML files for you. So it's a pretty easy way, because you don't have to, if you keep this documentation separate, you're never going to update it. If you keep it in the comments in the code, there's a better chance you'll keep these up to date as you change the code or write the code. That's sort of the idea of Doxygen. And within Atmel Studio, it has support for it. I was hoping to demo that live, but my other computer's having issues right now, so that'll be for later if you want to see it. But there's a whole configuration document. So, and I'll push this to Monday quickly about the GitHub stuff because of the delays. But very briefly, there's a lot to learn on C. We have some time to go through it. You'll have a lot of support in this class. The most important thing is always breaking down the problems to verify your code. So as you're writing different modules, to verify individual modules, make sure the rangefinder function is always working. Don't just say, oh, it worked once, great. Never look at it again. Because that's going to bite you when there's some weird error that only comes up ever so often. And Yeah, and we'll talk about how you use debugging for that. And there's also resources such as PC-Lint for testing code. So in this case, we're doing it in small chunks at a time, but you can still put in a large function if you want right into that tool to get an idea if you introduce some weird errors. And question, yeah?
Are there any Unix tools to use in place of Atmel Studio?
Any tools what, sorry?
Any Unix tools to use in place of Atmel Studio?
You can, yeah, so you don't need, are you using Mac or Linux?
OS 10, Mac.
Okay, yeah, so all of the tools, basically the Atmel Studio stuff, you know, I think it's just Windows only. I haven't even looked if they have a Mac version. But it is entirely, go back to it, it's entirely GCC, AVR GCC. So you can either compile everything if you want, like compile AVR GCC, but there is, I'm almost positive there's distributions for Mac. I haven't used the Mac ones, I've used the Linux ones a lot. Yeah, there's Linux ones. Like the only difference is that you'll have to do stuff through what's known as makefiles.
Yeah.
So you don't have a pretty a graphical interface for everything. It's the same when it gets down to it. It's
But so you can load up to the ship from.
oh yeah, everything should work. The only thing that I don't know if works is the programmer for the like for the robot device itself, because Mark wrote that. So I think it might be Windows only. I don't know. So if you don't have anything like VMware or Parallels or something, as a way around that, you can get, I'm pretty sure DesignSpark has some sort of Windows licenses, or at one point we had Windows licenses you could get here.
I'm not against
Huh?
stealing it for the course.
Okay. But yeah, so if you run that in a VM, then you can use the programmer. I don't know for sure. You may not need it. I'm pretty sure AVR Dude would support it. I can check with Mark. I just don't know offhand. But yeah, everything should be possible, basically. They don't?
You can get Windows 8.
Windows 8, okay. I don't know if his tools work with Windows 8 is the only thing too. I'm not sure. They should. It's just like an FTDI. It's a pretty standard thing, so I think it works. They do?
I think so.
Okay, I've just never tried it, and so Mark hates Windows 8, so I don't. Yeah, other questions I saw? No?
Yep.
Okay. That's it.